there, class. Welcome to Factoring Refresher. So we've been solving quadratic equations, and we've been using methods like the completing the square method, the quadratic formula, and graphing, but some quadratic equations can be solved using factoring as well. So in order to use factoring to solve, we have to make sure that we freshen up our factoring skills, and we're going to do that today. And we're going to start off taking a look at some really basic factoring methods, and then we'll kind of move to a level where we'll kind of combine some of these different methods together, and hopefully eventually it'll lead us to be able to solve quadratics and even higher degree polynomials, polynomial functions with factoring. So the most basic kind of factoring that we're going to be doing is called greatest common factoring. And you remember, doing greatest common factor with numbers. So for instance, if I ask you to tell me the GCF, or the greatest common factor of 12 and 18, what you're trying to figure out is what is the biggest number that divides into both 12 and 18 at the same time evenly. And so in the case of 12 and 18, we know that 6 is the greatest common factor. And so if we were to factor out the greatest common factor out of 12, we would get 2, and we would take the 6 out of 18, and of course we would get 3. So we have some background with greatest common factor, but how do you do that with, say, a polynomial? For instance, with question number 1, 12k minus 18, well, how do we find the greatest common factor? Well, we are going to treat the numbers different than variables. And notice only the first term here has a variable, the k, so they don't have a variable in common. So in this case, I'm not going to be able to take out anything other than just that greatest common factor of the coefficients, which is a 6, so I could write this as 6 times. So when I factor that out, in other words, I'm actually dividing out of each one of these terms a 6, and that would leave me with 2k left over and minus 3. So in effect, this is like using the distributive property backwards, which is exactly what factoring is. It's taking from expanded form into what's called factored form, where it's a product of two or more things, sometimes in this case like a coefficient and a binomial, that if you were to distribute it back out would give you the original polynomial. So taking a look at number 2, notice that there's numbers and there's variables in both terms, and so to start off, you would just kind of look at, to find the GCF, what is the greatest common factor of the numbers of 40 and 64. And right away I am thinking of 8. 8 divides into both of those evenly, so I know if I were to divide that out. But then each of those terms also has x's and y's. But as far as GCFs when it comes to variables, what you want to do is if they have a shared variable, then you can only take out whatever the lowest exponent is in any of the terms, and that's because that's all they have to give. Like for instance, this second term only has x to the 4th. It only has 4 x's to give, whereas the first one would have 8, but I can't take more than what I have, so I could take an x to the 4th out of both of these. In other words, I'm dividing out an x to the 4th out of each of these terms. And then as far as, the y's go, each have a y to the 1st, so I could divide out the y out of both of those. And so when I write this in factored form, whatever's left is going to go in the parentheses, and that's whatever's left when I divide 40 by 8, which is 5, and then when I divide x to the 8th by x to the 4th, that means I'm canceling off 4 of those x's, leaving me with x to the 4th. And of course, I don't have any y's left at all because they both, there was just one on top, one on the bottom. And then in the second term, it's a plus, I have 64 divided by 8, which is 8. And then, of course, the y's are going to cancel, and then the x to the 4th and the x to the 4th are going to cancel, so there are no variables left in that second term. So just 8x to the 4th y times 5x to the 4th plus 8 would be the factored form. Let's go ahead and try one more, and then we'll leave one for a you try. And so then you can pause it, try it, and turn back in to test your skills. So taking a look at number 3, I see that the coefficients are 14, negative 35, and negative 7. And by the way, let's say that the first coefficient had been negative 14 instead of 14. What I'm always trying to make is my leading term, whatever the very first term that's listed, it'd be positive. So if that's the case, if you have a negative term that's leading off, always try to take a negative out as well. But in this case, the leading term is positive, so I know that every one of these is divisible by 7, so I'm going to divide out a 7 out of each of the numbers. And then as far as the terms go, or the variables go, each one of them has m's, but the largest value I could possibly take out of every single one of those is the smallest that the last term has to give, which is m to the second power. So actually, I could take out 7m to the second power out of both. And again, what I'm really doing is I'm dividing every term. I mean, if it helps for you to write this out like this, what you're doing is dividing every term, well, hopefully writing it better than what I'm writing right now. But anyway, so I'm going to divide out a 7m squared out of every term, and then what's left is going to be in the parentheses, and that's going to give me 2m to the fourth, because I had 6 m's to begin with, and I canceled 2 of them out, and then minus 5m. And then finally, out of the last term, if I divide negative 7 by 7, I get negative 1, and of course the m's cancel because there's m squared and m squared. So that's just minus 1. Let's go ahead and pause the video, and you can try number 4 as a you try. So pause the video now, give number 4 a try, and tune back in to check your answer. Okay, so thanks for giving that a try, and hopefully this is what you got. Okay, so now we're going to go ahead and we're going to move on and take a look at some simple trinomials and see if we can factor them. So when I say a simple trinomial, what I really mean is one that starts off with just plain x squared. And we'll build to when they start off with something other than that. But if there was some coefficient in front of the x squared, then I would always want to look for a GCF first. The first few we're going to look at will not have that, won't have a greatest common factor that I can take out of any of these terms. But that's always kind of our plan, is if we can do this GCF factoring that we just talked about, maybe we can break what's left down and then it makes it a little easier to factor what remains. So, but these are really simple trinomials. For instance, the first one is x squared plus 14x plus 45. And you can kind of liken what we're going to try to do here with factoring to like basically reverse FOIL. So what we're trying to do is we're trying to think about if I had 2 binomials, it's called binomial factoring, and I'm trying to think about what 2 binomials I could multiply with FOIL to get back to x squared plus 14x plus 45. Well, first of all, because this starts off with x squared, there's no other way for these binomials to start than both have an x. Because, you know, when you do FOIL, the first 2 multiply x and x, you'd get x squared. Now they have to end with 2 numbers that multiply to 45. Now there's lots of numbers that do that. There are, you know, not lots of numbers, but I mean like 9 and 5. You could also go with negative 9 and negative 5 because they both have the same sign. It would still multiply to positive 45. It could be 45 and 1 or negative 45 and negative 1. And, you know, sometimes you have lots of different combinations. So how do you know which ones to choose? Well, they not only have to multiply to give 45, they have to add to give the 14 that's positive. So that first combination I talked about, the 9 and 5, where they're both positive, that would be the one. So that would be a x plus 9 and a x plus 5, or whichever one you want to write first. But that way, these 2 things, they multiply to give me that 45, but then they add, when I do the outside and insides for FOIL, I could see they'd give me a 9x and a 5x, which would add to 14x. So again, they're going to have to multiply to give the last term and add to give the middle term, which 9 and 5 fit the bill for both. They multiply to 45, they add to 14. And that's called simple binomial factoring. And again, I'm hoping this is very familiar to you from Algebra 1, but this is just a refresher, and then we might build to some more complicated ones than you've done in Algebra 1. So the next one, w squared minus 15w plus 26. So I'm going to start off my format because I know I'm trying to do binomial factoring because I have a trinomial. And of course I don't have any GCFs. I can take out no common factor for all the terms. So I know my binomials will both start with w, and they're going to end with 2 numbers that are going to have to multiply to a positive 26. And what that means is that they're either both going to be positive or both going to be negative. But because they have to add to this middle term negative 15, I actually know they're both going to be minus. So now I'm just looking for factors that do that. So let's see, 26, I think of 26 and 1 and 13 and 2. And there you go, 13 and 2 fits the bill as long as they're both negative. Negative 13 and negative 2 would add to negative 15 and multiply to positive 26. And it doesn't matter which binomial I write first, so I could write it as w minus 2 times w minus 13. Either way, they mean the same thing because it's just multiplication. So with 7 and 8, we're going to go ahead and have you pause the video. Actually, you know what, I'll do one more with you because I notice 7 is a little bit different. So again, I've got a trinomial. It starts off with c squared. So I'm going to go ahead and I know that both my binomials are going to start with c. They're going to end with two numbers that multiply to negative 48. So this time, one's going to be positive and one's going to be negative. And so when I think about factors of 48, well, the first ones that come to my mind, so I just kind of do a guess and check, you know. There's like 12 and 4, and there's like 6 and 8 and all that, but I know they have to be 2 apart. So I think of 8 and 6, and I know to multiply to negative 48, 1 has to be negative. Well, in order for this to add up to positive 2, if I made the 8 positive and the 6 negative, then they would do that. So it's going to be a c plus 8 and a c minus 6. So when that last term is a negative, you know that one of your binomials will be a plus binomial and the other one will be a minus. So then you just kind of play around with making one factor positive, one negative, until you can get them to add to that middle term. In this case, it was positive 2. Okay? So let's go ahead and pause the video and make number 8 be a U try. And so pause the video now. Tune back in a second to check your answer. Okay, so thanks for giving that a try. And that the two factors are n minus 9 and n plus 8. Negative 9 times 8 is negative 72, and negative 9 plus 8 is negative 1. So let's move on. So since you got that one right, hopefully, or if not, you figured out your error, let's make 9 and 10 also some U tries. Just give you a little more practice and checking in and make sure you're right. And then we'll try 11 and 12 together. So let's pause the video and, pause the video and let's try 9 and 10 as U try videos again, or U try problems, excuse me. U try question for 9 and U try question for 10 again. Pause the video, give them a try, tune back in to check your answers. Okay, so I hope that you noticed that on these two U try questions, that when you factored this, maybe you already recognized this right before you even tried to factor it, but that you're going to get identical binomials because those original trinomials are perfect square trinomials. And when that happens, your binomials will always be the same. So I had an a plus 6 and another a plus 6, so I could write that as a plus 6 squared. And we've been using that fact as we've been completing the square. And then for number 10 as well, that's a perfect square trinomial. So you could write this as n minus 1 squared. Okay. So in the event that you have identical binomials, you can always just write that as the binomial squared. Okay, so what's clearly different about 11 and 12 is that they don't start off with just k squared, x squared, n squared, whatever. 11 starts with 2k squared and 12 starts with 5z squared. Well, sometimes you can remedy that real quick. You could go ahead and divide that right off and you know, simplify that. In this case, in number 11, we could just divide everything by 2 and we could rewrite this as 2 times k squared, minus 8k minus 20, and then we could go ahead and you have to make sure you carry that 2 down as part of your factored form, but now you could go ahead and factor the remaining k squared minus 8k minus 20. So again, just this way they're both going to start off with just k, but then they're going to end with two numbers that multiply to negative 20 and add to negative 8. So let's see, the numbers that I think do that would be negative 10 and positive 2, and that's going to work. And so the factor form this time has a coefficient out in front. And you do have to have that 2 there because it does have to multiply back eventually to give you that original polynomial to be equivalent. So if you do have to take a GCF out, be sure to include it in your final factored form, which is this right here. That's your final factored form. Okay. So let's set this one as a U try. Give that one a try looking for the GCF to take out first, and pause the video now to complete number 12. Okay, so thanks for giving that one a try. So I factored out the 5 out of every term, leaving me with z squared minus 5z plus 6. And since the last term is a positive 6, we know that the both binomials have to be the same sign, and in this case they both have to be minus because they have to add to negative 5. So z minus 2, z minus 3 works with along with that 5 as the coefficient out in front. Okay, so let's take a look at number 13. So what if, like in number 13, you see, I can't divide that 2 off. So if I can't divide that 2 off, then what am I going to do? Because that just means that my binomials now are not both going to start off with just x. One of them would have to start, say, with 2x, and the other one would have to start with x. Or if there was some other different factors for 2, which they're not in this case, but if, say, that number was, 12, then maybe one could start with 3x, another with 4x, one would start with 2x, and the other with 6x, or whatever. And so now it's a little more complicated because that middle term is now not just determined by whatever the factors of the last term or the C are. So then we have to use a method that we like to call the AC method. And so we're going to go ahead and take a look at the AC method now. So first of all, this AC method I'm talking about, the AC method really is still just a guess and check method, just like we were doing in the prior trinomials. It's just that it's kind of an organized guess and check. And so when I call it the AC method, what I mean is I'm targeting the A and the C. And instead of just looking at the last term to figure out how I'm going to, determine those values in my binomials, I'm going to first start off by looking at the product of whatever the A and the C is, because that middle term is now going to be determined by both of those factors. So when I multiply 2 times 18, that's 36. So now what I'm trying to do is I'm trying to find factors of 36 that make the middle term. So I'm trying to focus in on negative 15 and get factors of 36 that make negative 15. Now that won't mean that's my final values that will go in my binomials, but at least that'll give me something to start with. So the factors of 36 that make negative 15, well, they have to be the same sign because 36 is positive. And then I start thinking about, there's 12 and 3. Well, that's the first one that came on. It's actually negative 12 and negative 3, but it could have been 9 and 4, negative 9 and negative 4. So they both have to be the same sign, and that means it's going to be negative 12 and negative 3. So negative 12 times negative 3 is positive 36. It also adds to negative 15. So now what I'm going to do is I'm going to take that trinomial and I'm going to turn it into a 4-term polynomial by splitting the middle term. So I'm going to take that middle term and I'm going to rewrite it as negative 12x and negative 3x. It doesn't matter which one I put first. So let's say I put the minus 12x and then the minus 3x and then plus 18. So I kept everything the same except for the middle term. I split up into 2 separate terms. Because what that allows me to do then, instead of looking at that trinomial as all 3 terms at the same time, I can do what's called factor by grouping, where I can just take 2 at a time. And so I could just ignore the second, the minus 3x plus 18, and I could just look at the first pair, and I'll do what's called GCF factoring, what we just learned to begin with, and GCF factor just out of those 2 terms. So I can see that both have a factor of 2, so I could divide out the 2. They also both have an x. The first one has an x squared, but I can only take out whatever the smallest power can give. So I could take a 2x out of both of those, leaving me with just x minus 6. And then if I look at the second pairing instead, now look at this pair, just independently, I could see that it starts off with negative 3x plus 18. Now remember when I said if it leads off with a negative, like this one does, you should always try to take out the negative also. Well, 3 and 18 have a common factor of 3, so I'm going to take out negative 3. So I'm going to divide each of these by negative 3. Oops, let's see if I can fix that. Which is going to leave me with a positive x and a negative 6. And then now you can see that they have this matching binomial. When I look at what I've got at this next line now, I have 2x times x minus 6 and then negative 3 times x minus 6. So that actually becomes a greatest common factor of those 2 terms. And I could say, okay, well, out of these 2 terms, I could take out the x minus 6. So then I could write it like this as the x minus 6 that I'm factoring out of that, and that leaves me with just 2x minus 3 left. And that's actually my factored form. This is, if I multiply this back, will give me the original 2x squared minus 15x plus 18. So we use this idea of factor by grouping because then that way we can focus on just 2 at a time. And instead of trying to think about all the combinations of factors of 2 and 18 that make 15, I can just look at it in 2 separate pieces. And then if I don't end up with a greatest common factor binomial like I did right here with that x minus 6, what it means is then I did something wrong or it's not factorable. Okay, and that's either one is a possibility. But more often than not, if it is factorable, that means that I just made a mistake. Now, what if I had chosen when I, at this level right here, and let's say I had chosen to write the minus 3x first and then the minus 12x, I'm still going to get the same factored form. It's just that that intermediate step, then the greatest common factor would have been 2x minus 3, and the numbers out in front would have been x minus 6. Let's go ahead and do another one. So again, I'm always going to check to see if I can take a greatest common factor out, and in this case I can't. There's nothing I can divide out of 5, 22, and negative 48, and of course they don't all have variables, so there's nothing I can do there. So I'm going to start right off with my AC method. I'm going to take the A and the C and I'm going to multiply them, and that's negative 240. So I'm going to think of factors of negative 240. They're going to have to be different signs. And I don't know, the first ones that come to my mind are the negative 24 and positive 10. And they're not going to be far enough apart. So I just get on my calculator and I start playing around with dividing negative 240 by maybe by 20. And when I divided by 20, I got negative 12. So maybe I'll divide by negative 240 divided by... So you just kind of keep playing around and dividing it until you get 2 numbers that are going to be 22 apart. And so I actually got a positive 30 and a negative 8 that multiply to give me this. And so I thought, oh, there you go. There's my sum of 22. So now I'm going to rewrite the trinomial into a 4-term polynomial. I keep the first and last terms the same. And so I'm going to start with a 5p squared. I'm going to end with a minus 48. But then the middle term, I'm going to split up into a 30p minus 8p or negative 8p plus 30p. And it doesn't really matter, again, which one you put first. I kind of just have a idea that having the 30p first fits better because I know I'm going to eventually pair these two up. And then minus 8p. So then I'm going to pair these two up, and I just think 8 and 48 go better together, and 5 and 30, but again, it doesn't really matter which pair. You're going to end up with the same factored form. So now I look at the first pair and I see what can I take out of both. Well, I could factor out a 5p out of both, and that's going to leave me with p plus 6. And out of the second pairing, I'm going to take a negative out because it starts with negative 8. So I could take a negative 8 out of both, and that's going to leave me with a p plus 6. Again. And if you have to, when you're first getting started, if it helps you to kind of just actually write what you're dividing out, out of each. Sorry, that's very messy. But then especially helps when you're dividing by negatives to realize if you have 2 negatives, it makes positive. So now you can see they have that common binomial factor, and so I can basically factor that out. And again, it doesn't matter which order you write this, but so one of the factors is p plus 6, and the other factor is going to come from those numbers out in front. So that 5p minus 8 is the other factor when I combine them together. 5p minus 8. And again, you can FOIL that back out and check it to make sure it's correct. And that's one of the really nice things about factoring is there's always an easy way to check it. You can just multiply back out, or in this case, FOIL it. Okay. So I'm going to do a couple more, maybe 1 or 2 more, and then we'll leave a few for you try along with the extra assignment that you have to practice. So let's see. I'm going to go a little bit quicker through it now. You can always rewind if you need to have it slow down. So I'm going to take the A and the C and multiply. I get negative 120. And then I'm looking for factors of negative 120 that add up to negative 19. So I just start playing around on the calculator, divide, I know that one's going to be negative, one's going to be positive, so I divide by 2 or divide by 3 or 4 and so on, and just until I get them so that they're 19 apart. And it didn't take long to find that it was negative 24 and positive 5. So those are the factors. And again, you're probably going to have to use a calculator for that. So I'm going to take and rewrite this with, I keep the first and the last terms the same, and then I'm just going to split the middle term up into a minus 24h and a plus 5h. And again, it doesn't matter which one you put first. So I'm going to do this, and now I've got a 4-term polynomial. So once I have 4 terms, I just split them up in 2 and 2, and I do my factor by grouping. And so I'm going to look for the GCF out of the first pair, and I can see you could take a 3 and an h out of those, leaving me with h minus 8. And then plus, and then I can take a positive 5 out of the second pair, so that would leave me with a 5, oops, sorry, an h minus 8. And then bingo, I see that they match, so I know I'm on the right track there. And so I just have to get my final factored form, and that's going to be the h minus 8, and then the 2 terms out in front make the other factor of 3h plus 5. And again, you can write either factor first, but that is the factored form. Okay, I'm going to do one last example with you, and I think this kind of brings up a kind of a special scenario that sometimes stumps students. So when I multiply the 12 and the negative 2, the a and the c, because I couldn't divide out the 12, I got negative 24, and I kind of went through some factors in my head. I know one's positive and one's negative because that's a negative 24, and I found 8 and negative 3 that would make that positive 5 that I need for the middle term to be. So when I rewrite it, the first and the last term stay the same, so that's 12x squared minus 2 off the n, and then I got to split the middle term. And so this time, say I chose to put the plus 8x first and then the minus 3x. And so now I've got 4-term polynomial, so I'm going to split it and just focus on 2 at a time. So when I look at the first pair, I can see that I could take a 4 and an x out of each, leaving me with 3x plus 2. And out of the second pair, I have a negative, so I know I at least have to take a negative out, because I said if the leading term is negative, take a negative. But other than that, like 3 and 2, they have nothing in common. So what do you do in a situation like that? Well, you have to take something. So if you can't take anything, you take 1 out. But in this case, because that leading term is negative, I'm going to take a negative 1 out. So if you can't take anything, always at least factor out a 1 or possibly a negative 1 if the first term is negative. So dividing each of these by negative 1 would then just change their sign to 3x plus 2. And now you can see we have that common binomial factor. And we could rewrite this then by listing the common factor as one of the factors. Again, it doesn't matter which one you write first. And then the other one will be the 2 terms out in front. They make your second factor of 4x minus 1. Now you can see, even just checking the first and the last, the first two, 3x times 4x makes 12x squared. And then the last two, 2 times negative 1 makes negative 2. And you can also clearly see that checking those middle terms, you got 2 times 4x, that's 8x. And 3 times negative 1, that's negative 3x. And 8x minus 3x is 5x, so it checks. Okay, so we're going to leave these 4 as you tries. You can give those a try, and if you want to tune back in, I'll just put the answer down there, not for work. But so pause the video, try those 4, tune back in, and you can check the answer. Okay, so here are the possible answers for 17 through 20. Now I said possible answers because on 18 and 20, there was potential to take out GCFs out of the terms. It didn't, in number 18, didn't really alleviate the major issue, but if you took out a 2 out of everything, it made smaller values to work with. But if you didn't, then you may have ended up with one of the other 2 listed forms. And on number 20, you could have taken out the 8 out of everything, but if you didn't, then that 8 could be distributed into one or the other of those 2 binomials. So you could have also had 8y plus 24 times y plus 4, or 8y plus 32 times y plus 3. So let's go ahead and take a look at the last kind of factoring, and that's difference of squares factoring. So the final type of factoring we're going to look at today is a special kind of factoring pattern called the difference of squares. And what you'll notice right away about all of these remaining problems is they're just a two-term polynomial. X squared minus 4, y squared minus 81, and so on. They're just two terms. And in all of these cases, also, they are a difference. So in other words, they're subtraction. And when you have this special situation where you have a binomial where it's a difference, and if the two terms are perfect squares, it results in a special kind of factoring pattern. And I mean, if we took a look at this x squared minus 4 and we kind of thought about it like the prior ones we were factoring, you could kind of think about it like this was x squared plus 0x minus 4. So that since there is no middle term, there is no x term, it's like that's a 0x. And if you kind of went back to how we factored those other ones, and we just said, oh, well, if it starts off with x squared, then both the binomials will begin with x. And they're going to end with two numbers. In this case, that multiplied to negative 4. But at the same time, they have to add to 0. Well, the only way you can add two numbers and get 0 is if they're opposites of each other. And so the two numbers that are opposites of each other that multiply to give us negative 4 are negative 2 and positive 2. So the special factoring pattern is that the binomials are nearly identical. The only way that they differ is by the sign. So instead of having to every single time rewrite this like it has a 0 middle term, if we just kind of train ourselves to look for this special pattern, when we have two perfect squares and a subtraction, it will always factor into two binomials that differ only in the sign, and the terms are the square roots of the two terms. So let's take a look at a little more difficult one in number 23. So in number 23, I have 9x squared minus 25y to the 4th. Well, first of all, the 9 and the 25 we recognize as perfect squares. X squared is a perfect square, but really any variable with an even exponent is also a perfect square. So this is the difference of squares pattern. And so if I were to go ahead and square root both the terms, my binomials would both have to start with 3x. And they'd have to end with 5y squared. And one will be a plus, and one will be a minus binomial. And it doesn't matter which one you list first. And that way, if you were to FOIL this back out, you would see that the middle term would just cancel. So it would just turn out to be a two-term or a binomial. Now, sometimes we might have a difference of squares special pattern, but it might be in disguise. So, for instance, taking a look at number 25, I notice right away that the variables are perfect squares. I have r to the 6th and s squared, but the 72 and the 2 I don't recognize from my perfect square list. But I do notice that they are both divisible by 2. So if I were to take and divide out the GCF, which is 2, and then simplify it, I get 36 r to the 6th minus s squared. And now I have two perfect squares and a difference. So that's a difference of squares. So when I factor this now, I'd have a 2, 6r cubed minus s and a 6r cubed plus s. So it's time for some U-tries. We'll leave the next column, 22, 24, and 26 as U-try questions. So you can pause the video now and try each of those. Tune back in when you're done to check your answers. So pause the video now. Well, thanks for trying those, and take a moment and check over your answers. And once you get done, if you have any questions, or things that you need clarification on, be sure to make a note, and you can bring that up when I see you in class. So, thanks for coming.